My name is Jessica Brysch, and I am a research engineer at Southwest Research Institute. I have over 8 years of experience at Southwest Research Institute acting as a project manager over research and testing activities. While designing test setups and projects, I also helped design the quality and safety system that is used across multiple organizations here at Southwest Research Institute. In the next hour, I'll introduce you to quality management systems. You see, they are a great way to promote safety, accuracy, and reliability. I think we can all agree that quality systems are underrated and frequently receive eye rolls because some of the record keeping can seem rigorous. But I'm going to show you some of the ways they can be applied to promote better business and safety practices, which is ultimately what I think we are all looking for. This, this webinar is intended for persons who are both new and experienced with quality systems, particularly to those who are looking to gain some examples of ways of controlling processes that help improve your product. This presentation is specifically geared toward research and development or testing, which are areas where you can't always compare the result you get with a known or expected value because there's not one. I'll give you some examples of ways that we control our testing processes and data to make sure the answer that we get the first time is the right one. Warning, I am not a trained quality system professional. I am an engineer. So this is more of a boots on the ground approach to applying a quality system within research and development. I've been helping to implement, improve, and monitor the processes within our quality system since 2012. Southwest Research Institute has its own group of quality professionals in our internal quality systems department. And that's who I reach out to when I need help interpreting standards and maintaining compliance. I'd also like to mention that the information presented in this webinar is specific to the Fluids Engineering Testing Program. The work performed at Southwest Research Institute is incredibly varied, and each business has different bodies with which they must maintain compliance. For this reason, there are many different quality management systems implemented throughout Southwest Research Institute. The presentation that you'll hear today is specific to third-party testing projects performed within the Fluids Engineering Testing Program. So, on to our agenda. First, we'll go through an overview of quality management systems and the ones that we use here at Southwest Research Institute. I'll give an overview of how research and development works compared to manufacturing to give you an insight about why applying a quality management system to research and development might be a little different, but still incredibly useful. We will move on to how we control the life of a project using what we call a project router, which is basically a checklist of everything you need to do to be compliant. Safety is a huge component in most businesses, and we'll discuss one of the many ways that a quality system can inherently promote safety practices. I'll also present 3 case studies of ways that we use the quality system to control different aspects of our business, including testing procedures, instrument calibrations, and in transparency through tracking of nonconformances. By the end of this webinar, you should have some really great and specific ideas of ways that you can boost the safety, accuracy, and reliability of your work processes. If you have more in-depth topics to discuss, my email address and phone number are available at the end of this presentation. If you boil a quality management system down to its most basic function, it is a collection of business processes focused on consistently meeting customer requirements and enhancing the customer's satisfaction. Essentially, it's about doing what it takes to achieve customer satisfaction. So aside from attaining customer satisfaction, why might you want to use a quality system? Well, this could be based on external requirements, such as a customer's requirement that you adhere to a certain standard for quality management systems, or it could be a government regulatory requirement that requires that you comply with a certain set of standards, or it could just be that you want to implement some aspects of a quality system to improve business practices and reliability within your product. Whatever the reason, your customers will thank you. To give you a little background about where or how we got to where we are today, we began with compliance to API Q1 and ISO 17025 because we were licensed with API to perform qualification testing on subsurface safety valves according to API standards 14A and API 6AV1. We've been licensed by API to perform these tests for over 40 years. In 2013, we expanded the scope of our quality system to include all third-party testing. And although we're not licensed, we claim compliance with ISO 9001. I'd like to give you the 10,000-foot overview of the documents we use to govern our quality management system. ISO 9001 can be implemented by any organization that provides a service or product. This standard is not specific to any product or industry. API Q1 shares a lot of similarities with ISO 9001, but it's geared toward the petroleum and natural gas industries. It contains additional requirements for documented procedure control and records of conformity. It also contains specific requirements for applying an API monogram to products or equipment for those companies who are licensed by API to provide an API monogram. And ISO IEC 17025 is generally used by testing and calibration laboratories. And while it shares the same intent as the other two standards, it is also much more specific about practices in record keeping, reporting, and procedures that must be followed in order to be compliant. When applying a quality management system to your business practices, the first thing you need to do is determine what your product is. Historically speaking, quality management systems are typically applied to manufacturing processes where your product is some tangible deliverable like a valve, a computer chip, or maybe a half a gallon of ice cream. In those cases, the quality management systems ensure that the product you produce is the same high quality product every time you make it. The manufacturing or production process is reliable and it's repeatable. As a research and testing facilities, we do not produce a tangible product. Our deliverable to our customers is data within a test report. So in defining that our product is essentially data, the quality aspects of our program are geared toward ensuring that the data we provide to our customers is repeatable and accurate and useful. Even though the test setup, the test procedures, and the test articles vary, we can ensure that our practices and documentation make the results we provide reliable and repeatable. One of the fundamental differences between research and development and manufacturing is that in manufacturing, you know what the answer is. If you make pipe spools, you can measure the ID and the OD and then look at the material certs, and you know whether your product is right or not. In research and development, you don't always know what the outcome should look like. It's important that all interested parties, from the customer to the mechanical designers to the test engineers to the persons performing the work, know that what you're doing might not be as historically known, the most efficient or effective or time-tested good old boys ways of doing things. So as the manager of a research effort, you need to help everyone to realize their value in a developmental process. This might mean having a short meeting to show them the next few steps in the process, or how what they're doing is fitting into a bigger picture. If your team knows where the process is going, they're more likely to help you get there. So with that in mind, our fluids engineering program has 4 managers, 16 engineers, if you include that all of our managers are also engineers, and 13 technicians. Without a quality system, you could request the same testing project of any of these team members, and the process by which they could go about solving the problem might be different. Documentation practices and storage of records could differ, and communication of stumbling blocks and lessons learned might get lost. When you're collecting records for a project, the goal is to maintain enough information about the test setup and conditions such that the same exact test could be repeated by a different project manager in the future. Although requirements for records are driven by our quality manual and operating procedures, we help ensure that the right records are collected using a project router. Our project router is a checklist that follows each project through the project initiation phase, the project duration phase, which is the testing phase, the reporting phase, and the closeout phase to ensure that all requirements of our quality system are met. This is also a good time to mention the relationship between the persons designing the quality management system and the persons required to adhere to that system. One of the worst things that you could do is to create a system with too many rules that's difficult to follow, or that creates unnecessary paperwork to shovel, or maybe it just takes too long to do everything. A good quality management system is a tool that helps its users to be successful. We hold a short meeting once a month to highlight the why of our quality system to its users so that they understand what's driving our goals and methods. It really helps with compliance because the users understand why they're doing what they've been required to do. Another trick that we've learned is to try out new processes and forms on project managers before they become official so that we can see if those forms or processes are efficient. We can also see if they're really horrible. And if they are, we can get input from the project managers who are required to use those so that when the new process is rolled out, they feel like it's more useful because they've had a say in the implementation process. I won't go through the router in detail, but I'd like to point out a couple of features in the project duration section. First of all, it's a step-by-step guide that reminds the project manager of all of the steps and documentation that are necessary in order to be compliant with the quality and safety requirements of a test. In addition, there are references to operating procedures and forms to make it easier for the project manager to review the quality requirements in detail or to find the required forms quickly. When a project manager has completed the project router, they can be sure that they have performed all of the necessary steps in order to be compliant. One of the great things about a quality management system is that it inherently helps to create a culture of safety. Our quality management system includes both the elements of safety and quality in one inclusive system because many of the documentation practices are the same. As such, the safety requirements for each project, such as management of change, job safety assessments, personal protective equipment requirements, and pressure containment design requirements, just to name a few of the many, are built into our quality management system. So let's go through an example of how a well-implemented quality system promotes good safety practices. At Southwest Research Institute, we have multiple permanent facilities that are adapted to perform a wide variety of testing on test articles that have different operating mechanisms, different performance characteristics, and different pressure ratings. In order to perform testing safely, the permanent facilities must be adapted to accept those different test articles. To maintain facility continuity, those adaptations are documented and communicated through our facility management of change process, which I will refer to as an MOC. So here you see a photo of our gas test facility. I'd like to point out our gas nitrogen source and our liquid nitrogen source. The gas nitrogen source remains between 2,000 and 3,000 psi. And I'd also like to point out our test section, which is configurable based on whatever item needs to be tested. This system was designed for pressures up to 3,000 psi, but it's also used for test articles that are rated well below that. And if you're interested in design for pressure control, Angel Weilman from Southwest Research has also posted a webinar on YouTube called Test Facility Design Techniques for Pressure Control, and you can learn more there. For any changes to this system, we would initiate an MOC. The changes we track can be permanent or temporary. So a temporary change would be something that would be implemented for the requirements of a single project, and the expectation would be that you return the facility to its original condition. Or a permanent facility change would be something that you implement that would last forever. Either way, we would fill out our management of change form and use the top portion to describe the change that will happen and whether it will be a permanent or temporary change. We'd also review the impact of change section so that we can tell whether any other documents or what will have to be revised or any other persons will have to be notified as a result of that change. And then there's also an approval section at the bottom where a quality representative and a safety representative within our quality system must review the change to make sure that it makes sense to our overall business quality and safety practices. Closing an MOC is a bit different for permanent and temporary changes. For permanent changes, the safety coordinator must confirm that the change has been physically implemented and that anything identified in the impact of change section, such as drawing changes, notifications to facility operations, updates to facility hazard assessments, or updates to lockout tagout documents, that those have been completed before the MOC is closed. If the change is temporary, the safety coordinator must determine that the facility has been returned to its original configuration before that MOC is closed. Let's look at the piping and instrumentation diagram for the gas test facility, which we've seen in the photo. Each component is labeled with a unique designator and pressure rating, and there's also a line size. So let's consider a case where we need to test a valve that's only rated to 2,000 psi instead of the 3,000 psi, which is the system's maximum operating pressure. The valve would be connected to the piping in the configurable test section, which we can see a little closer here. The valve has to be protected from overpressurization by, we would limit the allowable pressures in our software, but we would also install an overpressure protection device upstream of the valve, like you see there. The P&ID would be marked up in this way, and it would be attached to a temporary MOC, which allows us to document and communicate this change to all personnel. The physical copy of this would be left in our control room so that it's available for anybody to see if there are any changes they need to be aware of in the facilities. Upon the completion of testing, the MOC reminds us to return the facility to its original configuration, like so that testing can continue on higher pressure rated test articles. And this practice also saves our ears from loud and unplanned pressure releases because we're not trying to go to higher pressures than what the system has been prepared for. The last thing I'll mention is that there is a line item in our project router that prompts the project manager to close out all MOCs before a project can be considered complete. This is one of the ways that we've designed our quality system to guide our safety practices. So next we'll move on to the 3 different case studies, and the first one that we will start with is procedures. When applying a quality management system to a body of work that varies so greatly, it becomes important to create and follow procedures. And I'm not talking about the kind of operating procedures that tell you how, excuse me, how you need to run your processes. I'm talking about testing procedures that provide specific instructions on how to perform a specific test on a specific piece of equipment. Test procedures should contain the following information. The first might be the most obvious, and that is step-by-step descriptions of the testing process. And while a detailed test plan is desirable, it doesn't have to be as painstaking as push this button and turn this knob. A good test plan gives clear instructions to the user, relaying the actions that need to be fulfilled. So here we'll follow an example for following procedures. So number 1, open the bypass valve. 2, start the pump to initiate flow. 3, adjust the pump to achieve 500 gallons per minute plus or minus 50 gallons per minute. 4, add sand to achieve a slurry of 2% sand by volume. And 5, allow to mix for 20 minutes, then take a fluid sample according to the sampling procedure. A step-by-step description will help make the test repeatable and ensures that all of the steps are performed in the same order each time. The next thing to consider is instructions for use and operation of non-standard equipment. There are times when a new piece of equipment is required to be joined with an existing facility in order to perform a test. This is the exception to the rule above. For equipment that is unfamiliar, you might need instructions that say, push that button and turn this knob. In the case of a testing facility, the non-standard piece of equipment could actually be the test article itself and whatever instructions are provided by the client on how to operate the hydraulics or electric controls that are required to operate the test article. Other things to include are instructions for handling and preparation of items where the absence of such instructions could jeopardize the test results. And I feel like this is a catch-all for the things that you need to know. But to give you an example, for a testing facility like ours, this might mean mentioning that the test article has to be installed and stored vertically during testing, and that it can't be stored or installed for testing horizontally in order for it to function properly. Another thing to do is to identify the test records. Identification of test records is about setting and then meeting expectations. This is the part of the procedure that serves to connect the expectations of the customer or whoever is going to be using the data that's being gathered, to connect that with the engineer who is designing the test setup so that the test setup has all of the capability to produce those records. And you're connecting both of those parties with the operator who will be responsible for following the test procedure and performing the work that will create the test results. If you can ensure that the expectations of all three parties are the same, there is a greater chance that your data will provide the right kind of value to its end user. Also, records are not limited to spreadsheets of data. You have to be creative about what it is your customer is trying to get to. And so other forms of records could be results from fluid samples that you send off to be measured for viscosity or chemical composition. It could also be photos that you take before and after of whatever you're testing. It could also be the test article weight. So if you were experiencing something like erosion, you can measure the weight of the test article before testing and after and get some sort of quantifiable result from the weights. So whatever it is, you should decide that with your customers, get approval on the methods for doing those things, and make sure that's included in your test procedure. And then the last thing is customer approval. And again, we're defining the customer as the person who will be using the data that you're getting. Obtaining customer approval for your test method ensures that everyone agrees on the goal and the methods of testing. The final point I'd like to make about procedures is that they provide some accountability. In a perfect world, you'd write a procedure, you'd follow it perfectly, you'd collect all of the correct data without any instrument or equipment failures. Mother Nature would cooperate with you, and then you'd repeat that test another 10,000 times the exact same way. This is most certainly not a perfect world, and while you can use some engineering or administrative tactics to eliminate some of the elements that might interrupt a test, there is always some combination of human error and Murphy's Law that will work against you. Our solution to this is nonconformance reporting, and let's be clear, nonconformances are not a way of snitching, and they should not be viewed as an indicator of bad performance. What they are is a useful tool that identifies a technical problem and that allows us to develop a solution of what we're going to do to solve it. In keeping with this mindset, we don't name any names in our reports, though we might say the operator or subcontractor to give the report a kind of context of, who's there and how much they know about the systems that they're working around. But we don't put any names because ultimately it's not about who did it. It's about how we're going to fix it and how we're going to prevent it from happening again. Our next case study is in instrument calibrations. Because the data that we provide in a report is essentially our product, we take the quality and the condition of the instrumentation and equipment that we use very seriously. For instruments, we define a required accuracy and an instrument calibration interval. The calibration results you see here are from Southwest Research's ISO IEC 17025 accredited calibration laboratory, where we send many of our instruments for calibration. Based on that same standard, we also calibrate many of our own instruments within our own laboratory, but that's another story for another day. So for instrument calibrations, we maintain a database where we keep a history of all calibrations performed and a list of every test with which an instrument is used. If that instrument returns out of its defined calibration tolerance, we can review each test and determine whether or not the discrepancy changes the results of the test. Now, I will say that most of the time we use instrumentation that is much more accurate than our test bands, and the results are not affected. But let's consider a case where the test results would be affected by the post-test calibration of an instrument. Each of our calibration records is reviewed by a project manager or a quality manager. If the results are unsatisfactory, like in this example of a leakage flow meter, the meter can measure flow rates up to 15 cubic centimeters per minute. All the test results that were obtained after the most recent intolerance calibrations up to the outer tolerance calibration, all of those would be reviewed. For each of the projects, we would determine whether the out of tolerance results were severe enough to affect any pass or fail results or any other results that were reported to a customer. This calibration result shows that the flow meter was out of its allowable limit. The allowable limit is 0.1 cubic centimeters per minute. It was out of that limit at 3 of the points at which it was calibrated. This would be recorded in our quality system as a nonconformance. This is what we would refer to as the as found calibration. And when this occurs, we ask the calibration lab to adjust the meter to see if we can get it back within its tolerance. The as left calibration shows the results after the instrument has been adjusted. In this case, you can see that the instrument is in calibration at all of the points. And at this point, we would most likely return this instrument to serve it, but watch it carefully for a while to see if there is a pattern of drifting. Drifting is what we would say happens when you adjust an instrument to back within its tolerance and it drifts out of tolerance over and over a couple of calibrations. If a pattern of drifting is identified, the instrument would most likely be discarded because we don't want to have to go back and we want to be able to trust our instruments. So for an example, let's say that this instrument was used on a test before it was discovered to be out of tolerance. Because we don't know if the instrument was used before or after it drifted out of tolerance, we have to assume that it was used in its out of tolerance condition. For example, let's say that in this test there was a valve that had an allowable gas leakage rate of 10 cubic centimeters per minute. In order for the valve to pass the test, it has to remain at 10 cubic centimeters per minute or less for, let's say, 10 minutes. This graph shows the original results of testing. Although the values are close, it clearly meets the requirement by the data. So let's go back and review the as found calibration. You can see that the allowable limit was plus or minus 0.1 cubic centimeters per minute, and that at the flow condition at which we were collecting data, which was really close to 10 cubic centimeters per minute, it's at 790% of the allowable limit. So let's save that information for the last point at the bottom of the screen, and let's see what the upper allowable limit would look like. The green line shows us the expected variability in this meter. When we send a report to a customer, we would tell them we measured this leakage rate and we would report that it is accurate to within plus or minus 0.1 cubic centimeters per minute. And so that means that any values from that blue line up to the green line represent the plus 0.1 cubic centimeters per minute of acceptable values that we report. Now this purple line is the actual flow rate. The blue line is the flow rate that we recorded and reported, but the purple line, according to the as found calibration results, is the flow that actually occurred during the test. In this case, you can see that the valve clearly did not meet the criteria of being less than 10 cubic centimeters per minute. Most of the time, we try to calibrate our instruments after a test, but before we provide a final report to our customer. However, there are cases when we must revise a report and resend data to our customer. Our quality system requires that we are very transparent with our customers about our findings, and we try to maintain the most accurate results, even if it means issuing a revised report. In an attempt to curb the likelihood that we would have to reissue a report due to skewed data, we also have a requirement within our system and a line item within our project router that requires all calculations to be checked by an engineer who didn't do the original calculations. Now, this isn't directly related to calibrations, but this is the type of calculation that we would perform on some of the data that we got out. And so it's another way that we validate our processes. In most cases, the point is to have the second person perform the calculations using different method from the original calculation. So if the original calculation was performed in a spreadsheet, the secondary calculation would be performed with a pencil and paper or MathCAD or MATLAB or Python or ANSYS, or you get the idea, something that's different, because if you can verify the calculation by two different methods, you can rule out some mistakes that can be inherently made with some softwares. Now, this doesn't fix the calibration issue, but it is another weapon for your arsenal of quality. Our final case study is on nonconformance tracking. So I mentioned nonconformances during discussion about procedures and then again in our discussion about calibrations. We use nonconformance reporting to record instances where our actions, equipment, or processes did not meet the intentions of our quality system. This practice has directly benefited our testing practices, facility safety, and even the economy of our business. And I'll show you how we track them. One of the most important things I can say about the general culture here has been curated by our management, and that is that no one is blamed for mistakes that are reported. All of our reports are scrubbed of names, which I've mentioned before. And I would say that even if you don't use names in reports, that some things could be specific enough that you know who it is, and management could still use nonconformances to judge performance. But I would say that our quality reporting system works because our managers really look on nonconformance reporting as an important part of the learning process. If people aren't telling you what kind of mistakes are happening, you will never have any idea about how to implement ways to prevent those mistakes in the future. Transparency and acceptance of mistakes creates a culture where employees are more free to tell on themselves without reprimand, and it ends up being for the greater good of your business practices. So, now with all of that said, what is a nonconformance? We classify nonconformances as any action or condition that does not conform to system policies and procedures. There are a really wide range of possible infractions, but some common ones include not following a test procedure properly, which would be an operator error, and this is one of those nonconformances that you would never catch without a culture of transparency and no blame. Um, Also, an out of tolerance calibration, as we discussed in the second case study, would also be recorded as a nonconformance, and also equipment failures that occur during testing, because a valve that doesn't actuate or a hydraulic pump that fails in the middle of testing, ultimately it'll have some effect on your test results and your test data. We also record safety infractions like failure to wear the proper PPE. That would be something that we would also enter into our system as a nonconformance. Every year we have a management review, which is also a requirement of our quality system. The purpose of this review is to inform management about the health of the business and to let them know what is or is not working about the system and to ask for help to change it. Having tangible records really helps build a case for change in your business. So we go through all nonconformances that occurred during the previous year and we group them into categories. Here you can see our main groups and an example of a nonconforming condition that might fall into that group. Each of these groups has many subgroups. For example, if we just look at Group A, when we track equipment issues, we further group them into out of tolerance calibrations, into equipment failures, also failure of customers supplied test articles. So we use these categories and then the subcategories to trend whether we are experiencing the same problems over and over. And if we are, we can address the root cause of that if necessary. This can be evaluated in a Pareto chart. A Pareto chart is designed to show categories with the highest to lowest occurrences. Within the lack of quality control, which is the A group or the D group, there were 8 instances of supplier failed to meet requirements. In this case, we would review whether there was one or multiple suppliers. If most of the nonconformances were caused by one supplier, we would consider whether there were other acceptable suppliers. If there were many different suppliers, we would look at the type of item that was being that was bought, and then if that was all the same type of item, let's say we buy a lot of sand that's required to have a certain kind of sieve analysis. If we had several different places that provided the same kind of sand, we might look at the requirements for that item and how we're interacting with our customers as part of a root cause. Within equipment failures, which is Group A, there were 7 instances of an out of tolerance calibration. We would look to see if this occurred on an instrument with the same serial number, and if it was all on one instrument, of course, we would discard that as necessary. If it wasn't all one particular instrument, we would look to see if it all occurred on the same type of instrument. So for example, let's say it was 3 different instruments, but all 3 of those instruments were a 0 to 250 psi differential pressure transmitter. then we know there might be some problem with the way that we are purchasing those or handling those. And in that way, we can narrow the problem down and see what we can do to solve it. The final category is group C, and that is the operator error category. And in this case, we had a data recording error. So here we would review each of the instances and see if there was something we could implement, like flashing lights that indicate whether data is being recorded. We've also implemented solutions like automatic background data recording so that you do have some sort of record. It might be a line item in the procedure at a certain point if that's where it's being missed. So you can see how we can look at whether a problem is recurring many times throughout a year and then find a way to solve that for the future. I think that knowing what your problem is half the battle. So you have to encourage good self-reporting and documentation practices in order to get results that will tell you where the holes are in your system. To bring everything back to making compliance easy, I want to point out how we did in reference to our project router. In this talk, we discussed test procedures and testing standards. We looked at management of change documentation. We looked at calibration of instruments, reporting of nonconformances, and double-checking data calculations. I've highlighted all of these items so that you can see how our router reminds us to satisfy these important components. It also shows you that we are required to track several more things than were covered in this webinar. Compliance isn't always easy, so I would encourage you to find ways to help your quality management system users to implement your quality system easily and effectively. In closing, I would like to mention that our friend Murphy is one of the greatest reasons to have a quality management system in place. When your processes and actions are well defined, there is a smaller chance that whatever can go wrong will go wrong. And that's particularly because within a quality management system, you are reducing and sometimes even eliminating what is even possible to go wrong. And as we always say, if you don't want to find mistakes, don't measure something twice, even though we often use redundant measurements within our test setups. And don't double check your data, which we also do. Through our quality system, we are committed to providing the best product possible, the best product being data. I would like to thank everybody for your time today, and I hope you found some valuable insights into how we apply quality management system to testing projects within the Fluids Engineering program here at Southwest Research Institute. And maybe you got some ideas about how to implement aspects of a quality system in your business model. Once again, I would remind you that I am not a trained quality management professional. I'm just an engineer who got thrown into a life of quality. So I would love to hear from you if you have any questions. My phone number and my email address are up here on the board.